Hello students, and welcome back to the channel. So in this video you're going to be starting differentiation. Now differentiation is going to be handled in separate videos. So for this video we are going to be looking at how we can find gradient of a function which is the same as dydx, and how we can differentiate from first principles. We also look at tangents together with normals in relation to differentiation. So the video is presented to you by Yusuf, and you advise to subscribe the channel, share the video to your colleagues so that you can all benefit as a family. Now before starting, we are going to first note down some of the most important factors that we need to understand before we start differentiating. So here, note number 1 is saying that it is important to understand that dy divided by dx is not read that way. It's not read as dy divided by x. Instead, it's read as derivative of y in respect to x. That's how I read it. That's why here I separated it. That instead of we are going to be writing it in this format, but you are going to be reading it as derivative of y in respect to x. So that's why dy dx means. Dy dx, if you are reading it or if you are making a presentation, it's read as derivative of y in respect to x. What is in the denominator indicate the function was differentiated in accordance to that parameter. Now let's look at the different examples. So we are going to be starting with first principles. But before we start first principles, your knowledge of polynomials for these following expansions has to be good. So you need to be understanding what you get when you have a square bracket of a plus b, and you need to be understanding what you get when you're having a square bracket of a minus b. You need to be in position of expanding these respective brackets, and to do that you need knowledge of polynomials together with quadratics, which was a topic already handled on the same channel. So now looking at the first question or the first example, we have told you that given that y is equal to x squared, find the derivative of y in respect to x from first principles, or find dy dx from first principles. Now looking at the solution, now for first principles, what you need to understand is that we are adding small changes, or we are adding errors that could have been present in that particular function. So we are going to get y, and then we add on an error of y, which is read as delta y. We also get x, and then we add on an error of x, which is read as delta x. So notice that here we have placed the delta x inside because the square component has to affect both the error together with its parameter. So after that, we are going to first expand this bracket, and on expanding that bracket, according to the polynomials knowledge of a plus b squared, of the square bracket of a plus b, you're going to get a squared, which is the same as x squared, then 2ab, which is the same as 2x delta x, and then delta x squared. I hope you have understood that. So what you're going to do here in the third step, on the third step, you're going to make small change in y the subject from this equation. To come here, we are going to make small change in y the subject. So remember that this is the bracket you have expanded, the three first terms. So we bring y on our right hand side, and it's going to be minus y. But remember, when you're starting the question, y was the same as x squared. So we substitute for y back. Now when opening up the brackets, you realize that x squared is going to go with x squared, because x squared minus x squared is going to give you 0. So we're going to remain with small change in y to be equal to 2x delta x, then plus delta x squared. So when you reach at this point whereby you cannot simplify any further, then we divide through every term by delta x, or by small change in x. So if you divide through this side by small change in x, you're going to get this. And if you divide this by small change in x, you're going to get 2x. And if you divide this expression by small change in x, you're going to get delta x, or small change in x. So here we are saying that after you getting this expression of small change in y divided by small change in x, then we bring in our approximation or our assumption, and this assumption is going to be based on that small change in x or delta x is going to tend to 0 when we are having an approximation of delta y divided by delta x also tending to dy dx. So if at all you have already got the sign of or the approximation of delta y divided by delta x on your left hand side, you can tend it to 0, but at the same time you also tend the small change in x to be 0. So if you do that, if this one becomes 0, you're going to get 2x plus 0, and small change in y divided by small change in x tends to dy dx. So you're going to make a conclusion that therefore our final answer is going to be equal to dy dx to be the same as 2x. And that's how you differentiate from first principles. Now let's first look at my examples to understand that properly. Now looking at example 2, we are supposed to differentiate from first principles the following questions or items. So part A, y being equal to 9x plus 5, and then part B, y being the reciprocal of x, and then part C, y being equal to 1 over x squared. So you're going to differentiate all these from first principles. Now remember, I told you that first principles is always about adding small changes or delta values of the respective parameters that you are dealing with. So if you pick up solution A, we are going to say that to differentiate that, we are going to add small change in y on the parameter of y. We also add small change in x on the parameter of x. Notice that you are using brackets since we told you that the error that you are adding must be attached to the parameter. So they must be in the same bracket. Then plus 5. So from here, we open up brackets and we make small change in y the subject. By bringing y, we bring y on your right hand side. And remember that y is the same as 9x plus 5. Now let's try to simplify that or to get it into details. So if you open up this bracket, you're going to end up with these first values, which is 9x plus 9 delta x. Then you bring also this 5, which is plus 5x. Now remember that to make delta y the subject this side, you're going to bring y on your right hand side. So it's going to be minus y. But remember that your y is the same as 9x plus 5. So what happens is that this negative, when it's opening up this bracket, it's going to make 9x to be negative 9x and also positive 5 to be negative 5. So in simplifying and collecting like terms, you see that 5 and negative 5 are going to cross. Also negative 9x and positive 9x cross, and then you remain with 9 delta x or 9 small change of x. Delta x and small change of x, they mean the same thing. So when you reach here, like we say that when you see that you cannot simplify any further, we divide through by small change in x. So dividing through by small change in x, you're going to end up with small change in y divided by small change in x to be equal to positive 9. So from here, after getting this delta y divided by delta x, we make our assumption. And our assumption was a small change in x, or as delta x tends to 0, also small change in y divided by small change in x is going to turn to dy dx. This was not supposed to be 0. Change it to dy dx. So from there, you conclude that therefore dy dx is going to be equal to positive 9. And that was the solution required for part A. Now let's look at the solution required for these fractions, if at all we are differentiating from first principles. Now looking at the solution for part B, we are also going to add delta or small changes to the given parameters. So y is going to be plus small change in y. Also x is going to be plus small change in x. So the next thing here is to make delta y the subject. And you have to do that by bringing y this side. So it's going to be minus y. But remember that your y is the same as 1 over x. That's why you are seeing this second step here. Now remember that in the previous videos, we told you that when you're adding or subtracting two fractions, we always find the LCM. So getting the LCM here is going to be x into bracket x plus small change in x. And you're going to end up with, according to the LCM that we discussed in the first videos, in the numerator, you're going to end up with x minus the bracket of this. So if you open up this bracket, it's going to be x minus x, and that is going to become 0. And then negative multiplies this positive delta x, and you get negative delta x in the numerator. So now you're having small change in y to be equal to this. So what is remaining is to divide through by small change in x. And if you divide through by small change in x, this one is going to go away. And then on the left hand side, we are going to have delta y divided by delta x. And on your right hand side, you're going to end up with this expression. Now we say that after getting delta y divided by delta x, you bring your assumption. As small change as delta x or small change in x tends to 0, also delta y divided by delta x tends to dy dx. And therefore, your derivative is going to be equal to -1 divided by x squared. Now let's look at the solution for part C. Now remember that all these ones are fractions and you are going to handle them the same way like we did to this one. So with this, we start by adding small changes to each and a given parameter. So y, we add small change in y, and also x, we add small change in x. You make sure that the power is outside the bracket. It should not be on the parameter. Then after doing that, we make sure that you make, now don't rush to open brackets straight away or immediately, especially in the denominator. So to do that, we have to make delta y the subject, so we have to bring y this side. And remember that y is the same as 1 divided by x squared. So that's why you ended up with this. So from here, we have to find LCM. And LCM is going to be x squared times this bracket. That's why in the denominator, you're having that. But you opened up this bracket. If you open up this bracket, you're going to end up with x squared plus 2x delta x, then plus delta x squared. And the denominator, or in the numerator, you're going to end up with x squared minus the square bracket of this, which we expanded and you go this. So if you open up this bracket, x squared and x squared are going to leave. And then you end up with negative 2x delta x, then minus small change in x squared, or delta x squared. Now when you reach here, if you look here, we can't simplify anything. So since we can't simplify anything, we divide through by small change in x, or by delta x. You divide only when you reach at a step whereby you cannot simplify further. So in dividing, we are going to end up with this side on the left hand side to be delta y, delta x to be equal to negative 2x minus delta x. Because if you look here, if you divide through by small change in x, if you prime factorize out here, small change in x, you're going to end up with this. And then this small change in x, one of the small change in x is going to go away with this delta x that we divided it with. That's why we ended up with this numerator. So the denominator remains unaffected. On reaching here, we say that when you're having small change in y, or delta y divided by delta x, we bring our approximation. So small change in x tends to 0. Small change in y divided by small change in x tends to dy dx. And after that, we make our conclusion. So you simply substitute where you see small change in x, you substitute with 0. And then where it says delta y divided by delta x, you put dy dx. So we shall make our conclusion that therefore dy dx is going to be the same as negative 2x divided by x power 4. But this x can be reduced. So for us to get the choice mark, we have to simplify our answer. So if you cross this x with this x power 4, you're going to end up with negative 2 divided by x cubed. And that was the final answer. Now let's look at solution for part D. So if you look at part D, we had a function that y squared is equal to x. Remember that for first principles, we add small changes on each and every parameter, and powers must be always outside the brackets. So it's going to be y plus small change in y to be equal to x plus small change in x. So we open up this bracket according to a plus b squared. And you're going to end up with y squared plus 2y small change in y, then plus small change in y squared to be equal to x plus small change in y. But remember that your x, when you're beginning, remember that your x is the same as y squared. So we bring it this side. It's going to be y squared minus y squared. That's why this y went. I hope you have understood that step. X is the same as y squared. So if you bring x this side, they are going to cross each other, and then you're going to end up with 2y delta y, then plus delta y squared being equal to delta x. So if you look here, Now we are going to make some changes or some approximations that may alter us or later. They are not so vital, but you need to understand them. For small angles measured in radians, when you're having an error squared, this approximation, you can also use it for other examples. When you're having two errors multiplying each other, we always approximate them to 0. So this one becomes 0, and then you are going to end up with 2y delta y to be equal to delta x. Now remember that we are looking for delta y divided by delta x, and the only way to get that is by dividing through each side by delta x. So this side you're going to end up with 1 because the delta x are going to cancel each other. And this side you're going to end up with 2y multiplied by delta y delta x. So if you have to make delta y delta x the subject, we have to take 2y this side. So it's going to be delta y delta x to be equal to 1 divided by 2y. But remember that y, if you go back to our question, we started with y squared being equal to x. So if you want to get y is going to be the same as root of x. So that's why I made the substitution that delta y delta x is going to be the same as 1 divided by 2 root of x. So after getting delta y divided by delta x, we can bring in our assumption. And then we say that as delta x tends to 0, also delta y divided by delta x tends to 0. So you're going to end up with our value of dy dx to be equal to 1 divided by 2 root of x. And that was the answer that was required. So you're going to pause the video and then you take a self-assessment exercise to test your understanding about differentiating from first principles. So I gave you enough items to test out your understanding. So make sure that you pause the video, share it to your colleagues if you haven't, and discuss together the assessment. So here we're going to make a simple note that when differentiating a function, we normally use variables given. Now if you're differentiating, for example, if you're having a function y is equal to cos x, then you're going to be differentiating in respect to x. Your value is going to be dy dx. And if at all we are differentiating y being equal to t squared minus 2t, since our function is in terms of t, our derivative would be dy dt, simply because our function is in terms of t. If at all we are differentiating y equals to sine theta, our derivative would have been dy d theta, and that's what this note is meaning. The derivative is not always dy dx, it's always dy in respect to what you're differentiating. If you're differentiating t terms, it's going to be dy dt. If you're differentiating a function in terms of theta, it's going to be dy d theta, among others. So if you're to make a summary of results, we're going to say that finding the gradient of any curve simply means differentiating. So the moment you find the derivative and then you substitute for the value of x, you have already got the gradient of either curve or a line. I hope you have understood that. So that's how we find gradients. Gradients are the same as derivatives after substituting for the value of x. Now with that knowledge, let's look at the direct differentiation. Now when you're differentiating directly, if at all you're differentiating in respect to x, because all these terms are in terms of x, so you're going to be having dy dx. When you're differentiating directly, we get the function and then we reduce its power by, first you get its power and then you multiply it by what you're going to be differentiating. So the power here is 2, that's why you bring it here. So you bring the power down and then you write the function and then you reduce the power by 1. So our function is x, it has a power of 2. So when you're differentiating, we first bring down the power and then we write the function which is x and then we reduce its power by 1. So 2 minus 1 is going to be 1. And that's why the derivative or dy dx of x squared is going to be the same as 2x. If you have understood first principles, you can test that out. If you look at the second function, if you differentiate directly, it's going to be dy dx, and this simply means that we have differentiated y in respect to x simply because our terms are in terms of x, or our function is in terms of x. So when you're differentiating directly, we get the 3, or which is the initial power. Then you write your function, which is x, and then reduce its power by 1. So 3 minus 1 is going to give you 2. Therefore, the derivative of x cubed is going to be 3x squared. And that's how it goes. Now let's look at another example. So for this example, we are prompted to find the derivative of part A, 3 quarters, or 3 divided by 4x squared, and part B, x power 1 over 3. We are going to follow the same procedure. So if you look at part A, I first started by making my function linear. Remember that in differentiation, we do not differentiate constants. What do I mean by constants? Constants, I mean values. 1, a half, a third, any value. We don't differentiate constants. So what we do is that we pull out the constants before we differentiate. So if you're having y being equal to 3 out of 4x squared, we first pull out the constant, and the constant here is going to be 3 over 4. And then in brackets, you're going to remain with your function, which is the same as 1 divided by x squared. Then later, we try to make our function linear. So to make the function linear, it's going to be 3 over 4 into brackets. Remember that in indices, when you take a function upwards, the power turns to a negative. So it's going to be 3 over 4 into x power negative 2. After making it linear, we can now differentiate according to the principles that we looked at. And remember that here the principles we looked at. So we say that we get the initial power before differentiating. So dy dx of that function is going to be 3 over 4. Then we differentiate our function, which is inside. So the initial power of our function is negative 2. So bring negative 2 here. Then times our function, which is x. Then we subtract 1. So negative 2 minus 1, you're going to get negative 3. Now if you multiply this and this, you're going to get negative 6. And that's why you're seeing here that I told you that if at all our function is this, the derivative directly is going to be negative 6 over 4 x power negative 3. So trying to simplify that by 6, if you divide through by 2, 6 divided by 2, you get 3. 4 divided by 2, you get 2. And then you end up with your final answer to be negative 3 divided by 2x cubed. Now you're going to do the same science with part B. So if you look at part B, the function was given as a linear function, so it was already direct, y being equal to x power a third. So differentiating, we are going to differentiate y in respect to x, or what you can call dy dx. So if you do that, we bring a third down, and then we write our function, which is the same as x, and then reduce our power by 1. So a third minus 1, you're going to get negative 2 over 3. And that's how we differentiate directly. That's why I told you that for part B, dy dx is going to be a third x power negative 2 over 3. Now remember that you have to take back this down according to laws of indices. So if you take this down, the power becomes positive. So it's going to be a third into x power 2 over 3, which can be written in this format. I hope you have understood that. Now looking at part C, the function is equal to x power negative a half. So to differentiate directly, we bring the power down, which is negative a half, and then we write our function, which is x, and then we reduce our power by 1. So negative half minus 1, you're going to get negative 3 over 2. Simplifying that, you're going to end up with this, as compared to the knowledge of indices that we looked at in the first video. Now for part Y, I think others are pretty direct according to the explanations I've given. Now let's go to the differentiation of a sum together with the difference of two functions. So here you're going to first note the following, that when y complies of more than one function, if at all y is equal to f of x and also g of x. The derivative is going to be, you first differentiate one function, you also differentiate the other, and the signs are going to vary according to the derivatives that you're going to be getting. And here we are going to be using direct differentiation. Now let's look at the examples that we can use to elaborate that. So provided that you have been given a polynomial f of x to be equal to 4x plus 1. Now what you need to understand is that every prime means a derivative on polynomials. So dy dx in terms of polynomials is written as a prime on that particular polynomial. If you're having polynomial of x, after getting its derivative, we call it polynomial prime of x. That's what indicates a derivative in polynomials. So if at all we are given these polynomials with different degrees. So if you look here, for us to differentiate part A, we differentiate directly. Now remember that I didn't talk about constants. When you differentiate a constant, you always get a zero. And what do I mean by constants? I mean a value which is not attached to any coefficient of any unknown. For example, 2. 2 is independent, it doesn't have any unknown like m, it does not have any unknown like x. So if you get an independent value, which is 2, 10, or anything that is not attached to any unknown or to any parameter, is called a constant. And whenever you differentiate constants, you get 0. Now whenever you differentiate a number which is attached to a constant, you are going to get that very number. For example, if you look at 4x, if you have to differentiate 4x, 4 is a constant, we pull it out, we don't differentiate the coefficient, we just differentiate the function which is x. So remember that x is the same as power 1. So if you have to differentiate this, first we pull down the power which is 1, so it's going to be 1, so it's going to be 4 into 1, then multiplied by x, then reduce the power by 1, so 1 minus 1 is going to be 0, so it's going to be 4 times x power 0. Now remember that any number power 0 is the same as 1, so it's going to be 4 times 1, and that's why we ended up with 4. That means that whenever you're differentiating any value attached to a parameter without a power, you're always going to get that particular value. However, we shall look at that more in details as we proceed with differentiation. If you look at part B, we have into x cubed, then plus x power half. So we differentiate these ones separately. So first, to show that we're differentiating, I put a prime on f of x to show the examiner that I'm differentiating. Now if you differentiate 2x cubed, according to what you have looked at, we say that don't differentiate the constants attached to the function. So we leave the constants out and then we differentiate our function which is x cubed. Now to differentiate x cubed, we have to bring this 3 down and then reduce its power by 1. So it's going to be 2 into 3x, then reduce the power by 1, is going to be 2. So that's why if you open up these brackets properly, it's going to be 2 times 3 to get you 6x squared. That's what you are seeing here. Now we also differentiate x power half independently. To do that, we drop the half and then reduce the power of x by 1. And that's how you get a half x power negative half. So simplifying that is going to give you 6x squared, then plus 1 over 2 root of x. And that was the solution that was required for part B. Now let's look at part C, how we can differentiate polynomial functions. So for part C, you're having u of x to be equal to x plus 1 over x. So we differentiate these ones independently. So the first thing that I did is to make everything linear. So this is going to be x plus 1 over x is the same as x power negative 1. So we differentiate each of them independently. If you differentiate x, you're going to get 1. Because it's going to be x power 0, which is the same as 1. And if you differentiate this, you're going to have negative 1 to drop, then x times x, then you reduce the power of x power negative 1 by 1, and you get negative 2. That's why you ended up with this answer. So simplifying this, making the power positive, we have to get a fraction, or we have to take x down, and then you end up with your final answer to be 1 divided by 1 minus 1x squared. So we do the same to part D. It's going to remain the same principle. Now let's look at another example that is going to involve quite advanced differentiation. So with this, we are going to be finding the derivative of different brackets or polynomial brackets that have raised to different degrees. So if you are to start with part A, we are differentiating x power the square bracket of x plus 3. Now to do this properly and easily, we first open up the brackets. Remember that I told you that you need to be very good at the expansion in polynomials or quadratics of square bracket of a plus b. So expanding this is going to give us x squared plus 6x then plus 9. Now remember that when you're differentiating, we differentiate each and every term independently. When you differentiate a constant, you get 0. When you differentiate 6x, or when you differentiate any number attached to a parameter, you get that particular value without the parameter. When you differentiate x squared, according to the lessons that you have had, you're going to get 2x. So if you go to part B, now for part B, we shall start by splitting the numerator or the denominator, because this shows that we found LCM before. So we split the two functions to take them back to their initial values. And after simplifying x squared divided by x squared, you end up with 3. Then x cubed divided by x squared, you're going to end up with 5x. So differentiating this function of y, which is 5x plus 3, differentiating a constant gives you 0. Differentiating 5x or any number attached to a parameter gives you that particular number. So you end up with your derivative of y to be equal to 5. So part C, part D, and part E were pretty easy. We use the basic knowledge. Differentiating that, you try it out and you see whether it gives you that. According to the principles, you put 4 outside and then you differentiate your function only. So differentiating 5x cubed, we drop the 3, which is a power, and then reduce the power by 1. So you end up with 4 into 3x squared. That's why you end up with 12, because 4 times 3 is going to give you 12x. And then you implement the same knowledge on differentiating each and every term in the other functions. So with that, let's proceed to the next part that's going to be about second derivatives. So after getting the first derivative, we differentiate for the second time, and that's how we are going to get the second derivative. If at all you have differentiated the polynomial for the first time, it's going to be 1 prime. So if you differentiate polynomial of f of x, we put 1 prime. This shows that it's the first derivative, or it's the first time of differentiating that polynomial. Now if you differentiate it 2 times, we put 2 prime symbols, showing that this function has been differentiated 2 times, or to call the second derivative for that function has been attained. Now let's look at the example. If at all you're having f of x to be equal to x plus 1 over x, let's find the first derivative and we also find the second derivative. So what the second derivative partially means, it means that you are supposed to differentiate for the second time. So provided you're having the f of x or function of x to be equal to x plus 1 over x, the first thing we do, we make it linear. So it's going to be in this format. Remember that you have already differentiated this. So differentiate x, you get 1. When you differentiate x by negative 1, you're going to get negative x by negative 2. And then we take it back to the fraction form to make the power positive, and then we are going to end up with the first derivative to be 1 minus 1 over x squared. Now to get the second derivative, we simply have to differentiate the first derivative. So to do that, we simply get this fraction which is linear, we bring it back here. When you differentiate any constant, you get 0. Then when you differentiate x power negative 2, let's try to differentiate this together. You're going to end up with negative 2. You drop the power and then reduce the power by 1. So it's going to be negative 2 into negative 3 power negative 3. But remember that also this negative is present. So this negative and this negative multiply each other and then you end up with 2x power negative 3. So to make this power positive on x, we take it down and it becomes 2 divided by x cubed. Now let's look at my examples to elaborate that completely. So if you look at part A, we are supposed to differentiate first time and the second time, of x squared plus 7x minus 6. Now differentiate for the first time. This is a constant, is going to become 0. This is 7x is going to become 7. Any value which is attached to a parameter, when differentiating it, we get that particular value. When you differentiate x squared, you're going to get 2x. So that's why the first derivative in part A is going to be 2x plus 7. Now when you differentiate the second time, we are going to call that d2y dx squared, showing that you have got the second derivative of y in respect to x for the second time. That's how we interpret it. So differentiating 2x, you're going to get 2. And then differentiating a constant, which is 7, you get 0. And that's why I concluded that, therefore, the second derivative of that function of y is going to be 2. So if you look at part B, differentiating x, you're going to get 1. And then differentiating negative 7x power 4, you're going to get negative 28x cubed. So when you differentiate for the second time, 1 becomes 0, and then this becomes negative 84x squared, and it's called the second derivative. Now we apply the same knowledge on part C and part D. You try to pause the video and you try to peruse through it to see whether you're understanding it or not. Now make sure that you address your concerns in the comment sections. Now let's look at the items that can be addressed, which may require getting specific values other than leaving our derivatives in terms of functions of x. So provided you have been told that find the value of the second derivative in case your value of x is going to be a, and the whole polynomial it must be equal to 24. So what you have to do is that you have to first find the first derivative of this. So x cubed, the derivative is 3x squared. Derivative of a constant is 0. So if you find the second derivative, which is going to be f2 prime x is going to be 6x, you simply differentiate 3x squared to get that. So from here, they have told us that the whole polynomial is equal to the whole second derivative is the same as 24. And where the value of x is, we substitute it with a. And they want us to get the value of a. So we shall do that. Where there is x, we put a, and then we equate the whole function to 24. And then to make a the subject, you have to divide through by 6. So 24 divided by 6, you're going to end up with your value of a to be equal to 4. And that was the answer that was required for that. Now the next example is going to be a proof, or what you can try to calculate to find both the first derivative and the second derivative. So what we need is our function. Our function was y is equal to 4x cubed. So the first thing to do is to get the value of dy dx. After that, we get the value of the second derivative. After getting that, we substitute it in this function to see whether our right hand side or our left hand side is the same as your right hand side. So if you handle the left hand side and then we substitute for our dy dx and our second derivative, you realize that you are going to have 288x power 4 then minus 288x power 4, which gives you 0. Now since the left hand side has given us 0 and also our right hand side is 0, then we have shown that y satisfies that particular equation. So with that, before you proceed to tangents and normals, I would ask you to first pause the video and then you try out this assessment to test your understanding from the beginning of where we started, and then we cross to tangents together with normals in relation to differentiation. So now let's proceed to tangents and normals in relation to differentiation. So you're going to first make a simple note that the gradient of a curve at any particular point P of that is going to be the same as the gradient of the tangent to that curve at any particular point, which is the same as p. Now let's look at that in examples. So provided you are given that f of x or polynomial of x is equal to this, and they want the gradient. Now remember that when I started in this video, I told you that gradient is going to be the same as the first derivative after substituting for the value of x. So we have to get our polynomial. For us to differentiate, we have to make it linear. So the first derivative, after differentiating this, we are going to get 2x. Derivative of x squared is going to give us 2x. And then derivative of x power negative 1 is going to give us x power negative 2 and negative 1. Then from here, we make the power positive by making the function a reciprocal. Then after that, for us to get the gradient, we have to substitute for the value of x. And in the points that are always given, the first coordinate is going to represent the value of x, and then the second coordinate is going to represent for the value of y. But majority of the times, the value of y is not going to be used. We are only going to be using the value of x. So we substitute for the value of x at this point, which is 1, in our derivative. And then we simplify using a calculator. We are going to end up with our gradient to be 1. And then we make a conclusion that the gradient of that particular curve at point 1 to 2 is going to be the same as positive 1. So the gradient is positive, and it also has a value of 1. So in example 3, or in example 2 under tangents and normals, so we are being provided the gradient of the curve, which is from this function. This function represents a curve. At a particular point is going to be 13. So they have given you the gradient to be 13. Now they want us to find the coordinates of point P. Now with this, they want us to find the values of x and y. But they have told you that the gradient is 13. But I told you that the gradient always comes from the derivative. So you have to get this function, and then you have to find its derivative. So derivative of 3x squared, you're going to get 6x. And derivative of x, you're going to get positive 1. Derivative of negative 3, since it's a constant, you're going to get 0. Now, since they told us that the gradient is 13, instead of dy dx, we equate our function to 13 because they are the same thing. So it's going to be 6x plus 1 to be equal to 13. We take 1 this side, it's going to be 13 minus 1 to give you 12. And then we divide through by, you're going to remain with 6x to be equal to 12. Then we divide through by 6. Then you end up with the value of x to be equal to positive 2. But remember that for us to get a point, we need the value of x, and you also need the value of y. So where are we going to get the value of y? So we go back to our initial function, because our initial function is the one which always gives us the value of y. So if you look at the initial function of the curve, is y is equal to 3x squared plus x minus 3. So after getting our value of x, we substitute for the values of x in the function of y, so that we can get the value of y, and this is what we did here. After computing everything in the calculator, you're going to end up with 11. So we make a conclusion that therefore the point is going to be 2 to 11, which was the one which was required by the item. Now looking at item 3, we are going to look at function of the curve y to be given by x squared plus b root of x. Now remember that a and b are going to be constants. So just that they're letters, but you have to treat them like we treat constants. So given that the gradient of curve C is going to be 5 at a point where x is 1 and then y is 1, we are supposed to find the values of a and b. Now first, since they talked about gradient, that means that we have to first find the first derivative. But as a reminder, remember that a and b are constants, so you treat them like if any figure which is 2 or 4. We are only supposed to differentiate x squared and also root of x to get the gradient or the first derivative. So implementing that, we are going to have y to be equal to, rewriting our function is going to be this. So since I don't want this square root, I will get rid of it by making it in terms of a power. So square root in terms of a power is the same as a half. So our function turns to this. So we have to find the derivative. Now remember that a and b are constants. So we ignore them and then we differentiate our functions, which is x squared and then which is x power half. when you differentiate x squared, you get 2x. And then 2x times a, you're going to get 2ax. And then when you differentiate x power half, you drop the power, which is a half, and then you reduce the power by 1, which is going to be negative half. That's why you end up with the second term as b over 2x power negative half. So to make this power positive, we take it down. We take the value of x down. So it's going to be x power half in the denominator, which is the same as square root of x. Because I've told you x power half is the same as square root of x. A half means square root. Now, since we have found the derivative, they told us the derivative is going to be 5. Then they gave us the particular points. The particular points they gave us, they told us that 1, x is going to be 1 when also y is 1. So we get our initial function, which is y, and then we substitute for the value of y, and we also substitute for the value of x, and then we simplify. So in substituting in our function of y, and then simplifying, we are going to end up with a plus b to be equal to 1. And this is going to be our equation 1. Then we also come to our derivative, which is this, and then we substitute for the value of x, and we also substitute for the value of dy dx. Now dy dx is the same as the gradient, and the value of x is the same as 1 from the points given. So after substituting for that, we are going to end up with 4a, and finding LCM, because square root of 1 is 1. LCM is going to be 2. When you get LCM and then you multiply through by the LCM, you're going to end up with 4a plus b being equal to 10. Now this is going to be our equation 2. Then we solve equation 1 and equation 2 simultaneously using the methods that we looked at under equations. So we are going to subtract 2 and 1, and if you do that, we are going to end up with 3a to be equal to 9. And if you make a the subject by dividing through by 3, you're going to end up with the value of a to be equal to positive 3. Then we use any of the equations, either 1 or 2, to find the value of b. And if you solve using equation 1, you're going to have b of b to be equal to 1 minus a, which is the same as 1 minus 3. So b is going to be equal to negative 2, which was the question requirements. And then we make a conclusion that therefore the value of a is going to be equal to positive 3, and then the value of b is going to be equal to negative 2, as required by the question. So that being covered, let's proceed to the next subtopic, which is going to be about attaining an equation of a tangent. Now here what we need is a given point together with a gradient. Nothing is complicated. So let's look at an example. So here we are telling you that find the equation of a tangent, which is a tangent to the curve y equals to x squared at a point which is 3 and 9. So we just need the gradient of that tangent. We already have the point. But remember that to get the gradient, when you're starting, we told you that the gradient of the curve at any point is going to be the same as the gradient of its tangent at that particular point. So to get the gradient, which is dy dx, we have to differentiate this curve. So that's why we wrote the function of the curve, and then the first derivative is going to give us 2x. Then we substitute for the value of x to get the particular gradient. Substituting for x being equal to 3, we are going to get our gradient to be equal to positive 6. Now after getting that, we find the equation of the tangent, and we are going to do that using the general equation y equals to mx plus c. So we first start by substituting for the value of y, which in this case is 9. We also substitute for the value of x, which in this case is 3, so that we can get the value of c, and we have got our gradient to be positive 6. And then after making all the substitutions, as per this step, we make c the subject using our calculator, and then you're going to end up with negative 9. After getting your value of c, we come back to the general equation, and we only substitute for the gradient and for the c, and then we leave y and x unknown. So it's going to be y equals to, the gradient is 6, we leave x unknown together with y, then plus our c, which is negative 9. So we make a general conclusion that therefore the equation of the tangent is going to be y being equal to 6x minus 9, as required by the question. So question 2 is saying that find the equation of the tangent to the curve having this function at this point. Then find the coordinates of the point where this tangent is going to meet the curve again. So we're going to first start by getting the derivative of the curve so that you can get the gradient. So at this point, the value of x is the same as -1. So substituting for that, your gradient is going to be equal to 2. So you have to get the equation of that partial tangent, which is got from y equals to mx plus c. And we do this so that we can get the value of c. So we have to substitute for the gradient, we substitute for the value of y, we also substitute for the value of x. So the value of y here is 1, the value of gradient, we have got it as 2, and the value of x, we have got it as -1, as substituted for here. So if you make c the subject, you're going to end up with the value of c to be equal to +3. So after getting that, we come back and we write the equation of the tangent after c has been got, but you don't substitute for the value of y and x. So it's going to be y is equal to 2x plus c, which is the same as +3. And that's going to be the equation of the tangent. Now for us to get the points where this tangent meets the curve, that means that both the curve and the tangent are equal at that point. Both their polynomials are equal at that point. If at all two things meet, for example, if at all I'm having two lines, y1 and y2, and I want to get the coordinates of the point of intersection, then the assumption there is that y1, or the equation of y1, must be equal to the equation of y2. And that's the same thing we do here. So you're going to say that if at all they are meeting at a partial point, that means that 2x plus 3, which is the equation of the tangent, must be equal to the equation of the curve, which is the same as 1 out of x squared. So from here, we get the LCM. Since the LCM is going to be x squared, we multiply through each and every element by x squared. So if you multiply through by x squared, you're going to get 2x cubed. If you multiply 3 times x squared, you're going to get 3x squared. Then if you multiply 1 by x squared, you're going to get 1. And then you bring it this side, then you get -1. So if you look here, we do prime factorize this function. Though this was a bit advanced, but we shall look at how we are going to simplify this after several topics, after covering another topic to show you how this was handled. But you prime factorize that equation and then we end up with this. And then we solve each bracket independently. Either this bracket is equal to 0 or this bracket is equal to 0. So the first bracket is going to give us x to be equal to 1/2. And then the second bracket is going to give us two values. It's a perfect square. So it's going to be square bracket of x plus 1 to be equal to 0. And then the value of x is going to be -1. So we end up with two values of x being -1 and also x being equal to 1/2. So since we're having two values of x, remember that you're looking for a point. A point has to have x and y. So we have to get the first value of x, which is 1/2, and then we get the corresponding value of y. We also get the second value of x, which is -1, and then we get the corresponding value of y. So let's do that. So you're going to use the equation of the, you pick either the equation of the tangent or the equation of the curve to get the corresponding value of y. So when x is equal to 1/2, if you substitute into the equation of the curve, you're going to get 4, because it's going to be 1 divided by 1/2 squared. And if you find the reciprocal, you're going to end up with 4. So it's going to be 1/2 and 4 as the first point. And if it's -1, you're going to end up with +1 as the value of y. And that's what was required. So let's proceed to the next part, which is going to involve attaining equation of the normal. Now remember that in your ordinary level, we told you that when you're relating equation of a tangent to that of a normal, is that a tangent is always perpendicular to the normal. So since they are perpendicular, the product of their gradients must be equal to -1. And that's why we made this note. Gradient of the normal times the gradient of the tangent must be equal to -1. So let's look at the examples to put that in details. So example 1, provided the equation to the norm of the curve, you're having a curve to be equal to y being equal to 3x squared plus 7x minus 2 at the point P, where x is going to be equal to -1. So you're supposed to first find the gradient of the tangent to this curve. because the curve and the tangent have the same gradients. So we are going to use this curve to get the gradient of the tangent, and then we use this formula to get the gradient of the normal. Then later we get the equation. So since we want to get the specific values or the specific points, we have to get the corresponding value of y at x to be equal to -1. So when you substitute for that, you are going to end up with a point to be equal to -1 and -6. So since we want gradient, we have to first find the first derivative. And the first derivative of this curve is going to be 6x plus 7. Then substitute for the value of x, you're going to end up with your dy dx to be equal to 1. Now this is the gradient of a tangent, but you want the gradient of the normal. So from this formula that m1 times m2 is equal to -1, if you substitute for the first gradient, it's going to be m2 to be equal to -1. That means that the normal is going to have a gradient of -1. So we are going to use this gradient together with the point that you have got to find the equation of the tangent or the equation of the normal to the curve. Now there are a lot of ways you can get equation of a tangent. One, you can start by getting y equals to mx plus c, and then you substitute for the value of y, you substitute for m, and then you substitute for x, and then you find the value of c, and then later you conclude that your equation is going to be in the following format. This was another method which involves gradient to be equal to change in y divided by change in x. However, they all mean the same thing, so you go with what you understand the best. Now let's also find the equation of the normal to the curve. These are the point where the curve cuts the y-axis. So the solution for that, we are going to say that, now remember that at y-axis, always x is equal to 0. So since x is equal to 0, we already have the coordinate for x, so we need the coordinate for y. So we simply get the curve and then we substitute for x equals to 0. So we shall end up with the value of y to be -8. That means that you are going to be using a point of 0 and -8. So for us to get the gradient, you have to find y dx, and then you substitute for the value of x, and our gradient is going to be the same as 0. Now since the gradient of the tangent is 0, when you substitute it into this formula of m1 times m2 to be equal to -1, you're going to end up with 0 to be equal to -1. And that's why we are saying that gradient of the normal is going to be infinite. And therefore, the equation of the normal is going to be approximated to be the same as the value of y, which is going to be -8, as you have calculated for it. Let's look at another example, and here we are saying that find the equation of the normal to the curve, this, which is going to be perpendicular to this line. Now we are going to go through this very fast. First of all, we are given a curve y to be equal to 24x plus 1, and the gradient in this curve is 24. Then the gradient of the normal to this curve, according to our theory, m1 times m2 to be equal to -1 is going to be the same as -1 out of 24. So this is going to be the gradient of the tangent, and this is going to be the gradient of the normal. So the gradient of the tangent is 24, and then the gradient of the normal is -1 out of 24. But then they told you that this, the curve that you are given, which is perpendicular to, is x cubed minus 3x squared plus 4. Now remember that a tangent can only be perpendicular to its normal, and that means that first, when you differentiate this, we have to get the gradient of the tangent. So differentiating x cubed minus 3x squared plus 24, you're going to end up with 3x squared minus 6x, and then you get this and then you equate it to 24. Now since you're having x squared and you're also having a lower degree without any other unknown, that means that this must end up into being a quadratic. So we end up bringing 24 this side and then prime factorizing out 3. So we divide through by 3 and then we solve this quadratic equation by factorization method, and then we end up with x plus 2 into x minus 4 to be equal to 0. So one value of x is going to be -2 and the other value of x is going to be +4. So we have to get the corresponding values of y on each of those x values. So when x is equal to -2, y is going to be -6. We substitute it into the equation of y. And when x is equal to 4, y is going to be equal to positive 20. And we make a conclusion that therefore both equations have an equation in the form which is going to be y to be equal to negative 1 out of 25x plus c. Now here we are going to be getting the equation of the normal, since negative 1 out of 24 was the equation of the normal. So we substitute for the value of y, and we also substitute for the value of x to find the value of c, so that we can get the first and the second equations of the respective normals. So substituting for the gradient y and x for this point, you're going to get your value of c to be this. And then we make a conclusion whereby we don't replace the values of y and x, and then we get the respective equation of the normal. And then we do the same thing when this one is equal to, when the point is 20. So we end up with the two equations of the normals as required by the item to be this and that. So with that, you're required to first pause the video and you take down the following questions for self-assessment on what you have picked in this video. So you pause the video for a second and then you take down those items. So that was it for this video. We'll meet in the next video that is going to be proceeding with further concepts under differentiation 1. Make sure that you like the video and share it to your colleagues so that you can all benefit as a team. See you in the next video.